In this video, we're going to be learning about how to convert between angular and linear quantities. We're going to start off with a short scenario. There are two elves walking around a stationary merry-go-round. The two elves are named Alfred and Bernard. Alfred begins at point A, as you can see on the circle here, and Bernard begins at point B. Both elves complete the circle within the same amount of time. What's the displacement, or the angle through which these elves travel? If you said 360 degrees, or 2 pi radians, you're correct. So both of these elves travel a displacement of 2 pi radians. What about the angular velocities of these two? How do they compare? Well, we know angular velocity is the angular displacement divided by time. The angular displacement is the same because they're going around one full circle. And it says they do it in the same amount of time. So the angular velocity of Alfred is the same as the angular velocity of Bernard. Which elf is moving faster? Let's take a look at the picture. Alfred's on the outer rim. Bernard's a little bit closer to the axis of rotation. Put yourself in Alfred and Bernard's shoes. If you had to go around this circle in the same amount of time, would you move faster as Alfred, or would you move faster as Bernard? If you said Alfred, then you're correct. How do you know? A lot of us may just know just from experience. If you're on the outside circle, you move faster. It's because you're covering a greater distance in that amount of time. A greater distance covered in the same amount of time means that you have to move faster. But we already established that the angular velocity is the same for both of them. So we must be talking about a faster linear velocity. Let's take a look at some of these linear quantities. We already learned something about the distance traveled. We learned that angular displacement is the distance traveled divided by the radius. Or, as you may otherwise see it, that the distance traveled is the angular displacement times the radius. Let's take a look at velocity. Don't worry about the name of velocity right now. We know that angular velocity is the angular displacement divided by time. And we know angular displacement is the distance traveled divided by the radius. So I have the distance traveled divided by the quantity radius times time. Well, I could write that as 1 over r times s over t. Distance divided by time. What is that? If you answered that that's speed, you are exactly correct. Distance divided by time is speed. So I'm left with v over r. We will more commonly write this as v equals omega times r, just as the angular distance equals the angular displacement times the radius. You'll notice a little pattern here. Before we move on to acceleration, I want to take a look at this velocity and talk about its direction a little bit. What is the direction of something that's moving in a circle? Well, here's an object moving in a circle. The green vector that you see is its velocity vector. Notice that it's constantly changing directions, but it always points in a very specific direction. That very specific direction is tangent to the path. If I drew the path of this circle, you would see that this arrow is always tangent to that path. That's why we call it tangential velocity. It tells us about its direction. Often we put a little t on there to remind us about that. What about tangential acceleration? Well, angular acceleration is the change in angular velocity divided by time. And angular velocity, we learned, is the tangential velocity divided by the radius. And if we're talking about the change in angular velocity, it's going to be the change in tangential velocity divided by the radius. So change in velocity over change in time. That means something. We call that acceleration. So the tangential acceleration is equal to the angular acceleration times the radius. Again, the direction of this the direction of this tangential acceleration is tangent to the path. Remember we learned earlier that every point on a rotating object has the same angular speed? Is that true for for tangential velocity? You should be answering no. That's not true for tangential velocity. It depends on how far you are from the axis of rotation. In other words, it depends on your radius. Let's take a look at an example problem that uses these equations. In this problem, we're talking about the rotors on a single engine helicopter. We're given the diameters. There's two rotors. The main rotor has a diameter of 7.6 meters. The tail rotor has a diameter of 1.02 meters. We're also given the rotational speeds in revolutions per minute. This wants us to calculate the speed of the tips of both rotors. Anytime a problem does not specifically say angular in front of speed, it always wants the tangential speed. So the equation that we will be using here is Vt equals omega times r. Let's start with the main rotor. That tangential speed is that angular speed times the radius. Well, the angular speed is 450 revolutions per minute, but we must convert that value. When I convert that value, I get an angular speed of 47.124 radians per second. I need to multiply that by the radius of that main rotor. Well, guess what? The main rotor has a diameter of 7.6 meters. Be very careful to read the problem. If it has a diameter of 7.6 meters, that means it has a radius of 3.8 meters. Plug those numbers into my calculator, and I find that a tip that is on the outskirts of this main rotor, or a point that's on the tip of this main rotor, has a tangential speed of 179.1 meters per second. That's going extremely fast. Now I'd like you to pause the video and figure out the speed of the tail rotor. The speed of a point that's on the tip of that tail rotor. For the tail rotor, the angular velocity is 433.33 radians per second. The radius is 0.51 meters, and this gives you a tangential speed of 221 meters per second. Let's move on to another example problem. This one talks about a car traveling at 29 meters per second, undergoing a constant negative acceleration after the brakes are applied. There are two things we want to know. How many revolutions each tire makes before the car comes to a stop, and the angular speed of the wheels when the car has traveled half the total distance. I'd like you to pause this video and try this problem, showing all your work in your notes. Then unpause the video for the correct answers. The answer to part A is 115.89 revolutions. The answer to part B is 62.14 radians per second. In both of these parts, you can choose to convert first, then use one of the 4 equations of rotational motion, or you can choose to use one of the 4 linear equations first, then convert. If you didn't get these answers correct, go back and try again until you do get these answers.